Hello everyone, welcome to this lecture on linear regression for the course Stat 3150 Statistical Computing. This will be a review lecture on linear regression. You should have seen linear regression in earlier courses. But here are the objectives. So learning how to fit a linear regression model using R, understand the output, and then compare and contrast with t-tests and ANOVA. So in the last module we talked about bootstrap and how to use it to approximate the sampling distribution. And I'll remind you the general idea was to replace the true CDF by the empirical CDF, which effectively is what you're doing when you're sampling with replacement. If we make assumptions about the data generating mechanism, we can actually sometimes improve on the general bootstrap. We can get smaller confidence intervals, for example. We'll explore this idea using linear regression, but first we'll review it. So we'll start with some general notation. The idea of linear regression, as you recall, is to estimate the relationship between a single variable y, called the outcome variable, and a series of variables x1 up to xp called the covariates. Y is typically assumed to be continuous, and just so you know, machine learning uses a slightly different terminology. So for example, typically y will be called a target, and the covariates will be called the features. Right, so the outcome y is typically continuous, like height, income, blood pressure, etc. But the covariates can be anything. We're not making any assumption about the type of variables that the x's could be. So we want to collect all variables on the same unit of observation, right? So for example, a person, a school, an animal, a type of olive oil, etc. So you can think of the y and the x's as coming as a vector. They're all measured on the same unit of observation. So we'll start from the basics. Simplest linear regression possible is one where you only have one parameter, the intercept, and no covariate actually. So this one will be equivalent to a one sample t-test, and we'll see how that's the case. The linear regression equation, when there's no covariate, can be written as the expected value of y is equal to some coefficient beta 0. And in other words, we're saying the population mean of y is equal to this particular parameter, and we're interested in estimating it. And of course, this notation is a bit overkill. We don't need two different ways we don't need two different notations for the same parameter. But it will make more sense when we add more parameters. So let's do a quick example first. We'll be using this data set, heart.csv, which you can find on UMLearn. It was originally downloaded from the UCI machine learning repository, if you're interested. There's more information on the data set there, but we'll be interested in looking at some of the variables in that data set. So first of all, we'll look at age as our continuous outcome. And remember here, we're not looking at any covariates at this point. So if you want to fit this in R using the function lm, what you need to do is lm of age tilde 1, right? So 1 here represents the intercept. And then you specify that data is equal to data set. If you do this and save the output into an object called, for example, fit, we can look at the output and we see our estimate for the single coefficient, which in this case is the intercept, and the estimate is 54.37. Remember, this corresponds to the average age in our data set. It's actually the sample mean in this particular case, but it's an estimate of the population mean. So an estimate of the average age in the population. To compute a confidence interval, we can use the function confint, and then we just write confint of the object fit. And when we do this, we get a 95% confidence interval for the intercept, or in this case, again, for the average age. Okay, so far so good. This was the simplest possible linear regression. The next simplest linear regression has a single covariate x, and we're even going to make a further assumption that it can only take two values, 0 or 1. You can think of this as encoding some sort of binary variable where, for example, male is 1, female is 0, or 1 corresponds to a student being a computer science major and 0 being any other type of major. In this particular case, the linear regression equation is a bit more complicated. Not too much, we're just adding one more term, so we get that the expected value of y given x, right, this is a conditional expectation. We write that it's equal to beta 0 plus beta 1x. That's the regression equation. So let's unpack this a little bit to make sure we understand. We're conditioning on the values of x. So let's look at what happens to the equation when we plug in the only two values that x can take, 0 and 1. First, if we plug in x equals 0, we get beta 0 plus beta 1 times 0. So in other words, we only get beta 0. So the expected value of y, conditional on x equals 0, is beta 0. And next, if we set x is equal to 1, we get beta 0 plus beta 1 times 1. In other words, the expected value of y given x equals 1 is equal to beta 0 plus beta 1. And so now we can actually interpret those two coefficients. Beta 0 represents the population mean of y when x is equal to 0. But beta 1 represents the difference in population means between the two subgroups. And so testing for significance of beta 1 effectively allows us to test for significance of the difference between the two population means. And so if beta 1 is significantly different from 0, then we have evidence of a difference in means between the two groups. And this should remind you of a t-test. And in effect, this is what we're doing here. We're doing a t-test, but in the guise of a linear regression, which is a more general framework. So let's look at an example of this. Now we have this one covariate. We'll look at sex. In this case, it's coded 0 and 1, so it's a binary variable in this particular instance. And we can fit this linear regression model by doing lm of age tilde sex, comma, data equals data set. And then if we look at the output of this, we get our two coefficient estimates. We get the intercept and we get the beta 1. And so the intercept, remember, represents the average or the estimate of the average age for the subgroup of observations corresponding to x equals 0. And then sex, or beta 1, is the difference between the two groups. And you can see here the difference is negative. So there's a negative 1.9 year difference between the two groups. Again, we can use the function conf_int to compute a confidence interval. We get the 95% confidence interval. And we can see that the confidence interval for the second coefficient, so the coefficient corresponding to sex, actually crosses 0. So it contains the value 0, which means that we cannot reject the null hypothesis of no difference between the two subgroups. Okay, now sex was coded 0, 1, but just to show you the flexibility of the LM function, let's look at what happens if we change the coding 0, 1 to something that you may see in a data set, namely male and female. So here I'm just transforming the data set. I'm replacing sex by this coding using strings. And so I'm setting sex is equal to if-else. If-else, remember, we start by specifying a condition. In this case, it's sex equals 1. And then we need to specify what happens if it's true and what happens if it's false. If it's true, then we output male as a string. If it's false, we output female as a string. Okay, so now we have a new data set where everything is the same except for the coding for that binary variable. And just to show you what happens if we run the same code as before, so lm of age tilde sex, comma, data equals data set, you can see that we still get the same output, but now the coefficient, the name has changed a little bit. So instead of being called sex, it's called sex male. but everything else is the same. The coefficient estimates are the same. And so you don't need to do the change. You don't need to change from 0 to 1 coding. You can use the string coding in your own data analysis. Okay, so let's summarize what we've done so far. We saw how linear regression connects the average value of an outcome variable with the covariates. And the important observation when we add that one covariate was that the regression coefficient was measuring the difference in means. And so this is similar to a t-test, a two-sample t-test. And this is effectively what we recover with this framework. Okay, you can try this on your own. You can pause the video and try this exercise. So using the same data set, determine whether average cholesterol levels are different between men and women. Okay, I hope you gave that exercise a try. Let's look at the solution quickly. What we need to do effectively is to change the outcome. So instead of looking at age, we want to look at cholesterol levels. So you had to look at the data set to try to find the variable name corresponding to cholesterol levels. And that variable name is CHOL, col. And so everything else is the same. We can run lm of col tilde sex, comma, data equals data set. And then we can use conf int to determine, or to compute rather, a confidence interval. And we can see here that actually the confidence interval does not include 0. And so we can reject the null hypothesis of no difference between the subgroups. So we do have enough evidence to reject the null hypothesis. Okay. Now let's move on to the next level of complication for the linear regression. Instead of a binary covariate, we'll look at a continuous covariate. So we'll look at a single continuous covariate X. The linear regression equation in this case will actually be the same as before. And so we can write still the expected value of y given X is equal to beta 0 plus beta 1 X. Just as we did earlier, let's unpack this a little bit. So when X is equal to 0, we get the same thing as before. So the right-hand side still simplifies to beta 0, and we get the same interpretation. Beta 0 is the conditional expectation of y given that X is equal to 0. But how can we interpret beta 1? Well, it's going to be a bit different here. We'll compare two values of X that differ by 1 unit. So we're going to look at X is equal to little x, and X is equal to little x plus 1. If we do this, we have the following. So first of all, at little x, we get the expected value is equal to beta 0 plus beta 1 x. And then at little x plus 1, we get beta 0 plus beta 1 times the quantity x plus 1. Now we can multiply through, and we get beta 0 plus beta 1 x plus beta 1. But beta 0 plus beta 1 x is what we got when we plugged in little x. So we can replace this by the expected value. And rearranging this, now we see that beta 1 is still measuring a difference in expected value. It's measuring the difference between the expected value of y given x at x plus 1 minus the expected value of y at x. And so it's measuring the difference between the expected values when there's a 1 unit difference in the covariate. And so beta 1 still represents a difference in population means. So what you have to be careful about, though, is that beta 0 represents the population mean of y when x is equal to 0. But this, depending on the data set, may not actually be possible. So for example, if x represents age or cholesterol, then x equals 0 is not typically a valid value. You can't have somebody without cholesterol at all. So their measurement will never be equal to 0. So you have to be careful about interpretation in this case. There may not be a valid interpretation. Okay, so let's look at an example. Here we're going to use age as our outcome, and now cholesterol will be the covariate. And we can run this regression model by using the same code as before, or similar code. We get lm of age tilde call, comma, data equals data set. And if we look at the output, we do see only two coefficients here. So we get the intercept as before, and then cholesterol, the estimate being 0.037. And remember, this corresponds to the difference in means for two subgroups. So the difference in average age in two subgroups whose cholesterol level differ by only 1 unit. And we can even compute confidence intervals again, and we see here that the confidence interval for cholesterol does not cross 0. And so here I wrote down a careful interpretation of those coefficients. So the estimated value of beta 1 is 0.04, which means that two groups of people from the study who differ in their cholesterol levels by 1 unit on average differ in their age by 0.04 year, or about 2 weeks, with the higher cholesterol level being associated with being older. If you read this out loud, then you may realize that maybe it would make more sense to run the linear regression in the opposite order, with cholesterol as being the outcome and age being the covariate. Otherwise we get this weird interpretation, but it's still a valid interpretation. Okay, and so I'm leaving this as an exercise to actually do the opposite linear regression and use this to determine the average difference in cholesterol levels for people in the study whose age differ by 1 year. So pause the video and give that exercise a try. Okay, I hope you had time to try. Let's look at the solution. You can see here that it's very similar code, it's just that we switched the order of cholesterol and age. So we get lm of call tilde age, comma, data equals data set. And now we can look at the estimates. The estimate of the intercept here would correspond to somebody whose age is 0. The cholesterol levels, age equals 0 doesn't really make sense in the context of our data set. All of the patients were actually adults. But the other coefficient being of age would correspond to the average difference in cholesterol levels between two subgroups whose age differ by 1 year. And again, you can look at a confidence interval, and we see that the value 0 is not included in the confidence interval, and therefore we can reject the null hypothesis. Okay, and I'm going to let you read the careful interpretation here. Okay. And now let's look at the final level of complexity that we're going to look at for simple linear regression. And it's what happens if we have a categorical covariate. So still just one covariate, but now it's categorical and it takes more than 2 values. So let's assume that we measured a continuous outcome y across different subgroups. And just for simplicity, we'll assume that we have 3 subgroups, but we can generalize this to any number of subgroups. And let's define a variable z that keeps track of which subgroup an observation is from. So let's say that just for the sake of example, our categorical variable will measure will capture the major a student is in. So we'll have z is equal to 1 for a CS major, z is equal to 2 for a psychology major, and then z equals 0 will correspond to every other type of major. And let's say we want to compare the average value of y between all subgroups. And the question is, how can we fit this into a linear regression? The solution here is to introduce what we call dummy variables. And what the dummy variables will do is they'll keep track of the values of z. So we'll define x1 such that it's equal to 1 if z is equal to 1, and 0 otherwise. And then similarly, we'll define x2 equals to 1 if z is equal to 2 and 0 otherwise. And so just to summarize this, you can put all of this in a table to keep track of the values of x1 and x2 depending on the values of z. So if z is equal to 0, both x1 and x2 are equal to 0. If z is equal to 1, x1 is equal to 1 and x2 is equal to 0. And then finally, if z is equal to 2, x1 is equal to 0 and x2 is equal to 1. So why did we do this? The reason we did this is now we can write the following linear regression equation. And that regression equation will allow us to measure the difference between all subgroups. So let's look at this. So we get the expected value of y is equal to, given x, is equal to beta 0 plus beta 1 x1 plus beta 2 x2. You can think of x as being a placeholder for all of the x's, so x1 and x2. So we'll do the same exercise we've done so far. Let's plug in z is equal to 0. If we plug in z is equal to 0, this means x1 is equal to 0 and x2 is equal to 0. And so the whole right-hand side of the equation simplifies to beta 0. Okay, so the expected value of y when z is equal to 0 is equal to beta 0. And now let's plug in z is equal to 1. Remember that we get x1 is equal to 1 and x2 is equal to 0. So the right-hand side simplifies to beta 0 plus beta 1. Now you can start to see why we wrote this way. Beta 1 now corresponds to the difference in expected value between z is equal to 1 and z is equal to 0. So it's still measuring a difference in means. And then similarly, if z is equal to 2, we get x1 is equal to 0, x2 is equal to 1, and so the right-hand side simplifies to beta 0 plus beta 2. And so beta 2 is also measuring a difference in means, and it's measuring the difference between the two subgroups z is equal to 0 and z is equal to 2. And then of course beta 0 still represents the population mean when z is equal to 0. So we get three coefficients, beta 0, beta 1, beta 2. Beta 0 is the population mean when z is equal to 0, and then beta 1, beta 2 measure a difference in population means. Okay, so let's practice this with the following example. So in the package GS Labs, there's a data set called olive, and that data set contains information about olive oils from 3 different regions of Italy. We have some olive oils from northern Italy, some from Sardinia, and some from southern Italy. And so we may be interested in the average levels of oleic acid in olive oils coming from those 3 regions. And so we can do this using linear regression. And you can look here at the bottom of the page, we get LM of oleic, our outcome, tilde region, which is our categorical variable with 3 levels. And then data equals olive. Olive is the name of the data set. If we look at the output of this, we get the following estimates. And you can see we get one estimate for the intercept. And then we get an estimate for region Sardinia. So that would be the difference between Sardinia, average levels of oleic acid in olive oils from Sardinia, compared with the level 0. The level 0 here is the missing level, if you will. It's northern Italy. And so negative 5.25 would correspond to the difference in average oleic acid levels between olive oils coming from Sardinia compared with olive oils coming from northern Italy. And similarly, we get a coefficient for the average difference in oleic acid levels between southern Italy and northern Italy. Just as before, we can still compute confidence intervals using the conf_int function. And what we get are the following ones. And you can see that both region Sardinia and region southern Italy, the confidence intervals do not include 0. And so in both cases, we can say that those 2 olive oils, that their average average levels of oleic acid are significantly different from the ones in the olive oils of northern Italy. Okay? And so I'm going through the interpretation here. I'll let you read this. This is a recap of what I just said. I'm going to point out, though, the last point here. So beta 1 and beta 2 are giving us differences between one region compared to a level region, a basic level region, which was northern Italy. But these confidence intervals unfortunately can't tell us whether the average levels are different between Sardinia and southern Italy. That's not a comparison that any of those coefficients are doing. And so you would need to do that comparison separately. We won't talk about this, but there are ways of measuring those differences for the missing comparisons. Okay, so that's it for the review of linear regression. In this slide deck, we introduce linear regression as a general framework for comparing means between subgroups. That's the idea you should keep in mind. That's what linear regression is about. And we saw how one sample and two sample t-tests are just special cases of linear regression. And then by introducing dummy variables in the end, what we essentially got is ANOVA as a special case of linear regression. So linear regression, you can think of it as a more general framework that subsumes all of those different methods. And in the next lecture, we'll discuss the assumptions behind linear regression, and we'll talk about how to assess those assumptions using residual analysis.